Okay, welcome everybody. I'm very happy that we have today Francesco Lin, who's going to speak about the geometry versus topology via Dirac operators. Before I forget, after the talks, we will go for drinks, and for those of you who want also dinner. I reserved a number of spots, but I want to see how many people will join, because maybe then I have to update this. So can I have a show of hands? Okay, okay. That's sort of my estimation. Francesco, the floor is yours.
Yeah, well, thank you very much for having me here. It's a great pleasure to be here in the Netherlands. So the first talk, both talks will be around this theme. So try to understand the relation between geometry and topology using the Dirac equation. So the first talk will mostly be an overview of the topic, more classical things from the 80s, in particular the work of Gromov and Lawson. And the second part will focus more on low dimensions, so 3D, and talk about more recent stuff. Okay, but I want to give you an overview of how one can do these kind of things. So maybe let me start by stating maybe the basic question behind the whole field, geometry versus topology in some sense. So suppose you're given a smooth manifold. Okay, I mean, possibly we will mostly think about the closed case. So what kind of Riemannian metric G does it support? What means? Okay, so for example, the basic question is like, if you put local constraints on G, so give global obstructions. Okay, and by local constraints, for example, you can think of curvature. If you know something about the curvature of the metric, does it tell you something? Can you have metric of a certain type given certain curvature conditions? So maybe the most the theorem that started this kind of question is Gauss-Bonnet, maybe. So look it up. It's from the 1850s. Okay, so if you have a surface. Okay, then if you integrate the Gaussian curvature over your surface with respect to the volume, you get a topological invariance. So this is phi. Okay, so this is the Gaussian curvature. This is a local quantity, and this is a global quantity. Okay, so this is the kind of question I'm interested in. So if you know something about how the metric behaves at any point, you can say something about the shape of the space, for example. Okay, so maybe to jump a few years ahead, a very important result in this kind of direction is Bonnet-Miles. This is from 1940s. Okay, so maybe this is Gaussian curvature.
Did Bonnet live very long, or is it?
Yes, I think maybe there was some proof that was not or something more general, and it was part of both. I don't look very deeply into this.
Okay.
Yeah, I think you live more than 90 plus 20. Yeah, I don't know. That's a very very good question. Yeah. So if you have a manifold, and say it's not complete, but it's not closed maybe, but it's complete. Okay, with richly curvature bounded below by a constant strictly positive divided by everywhere. then this implies that M is compact. Okay, so you cannot have a non-compact manifold with Ricci curvature strictly bigger than 0.001 everywhere. Okay, so in particular, if you think about taking covering spaces, by taking covering spaces, this implies that if you have a manifold MG with Ricci positive, then the phi one of them is fine. It's fine. Okay, because otherwise you can, these are local conditions, so it holds for any covering spaces, and otherwise you will be able, if it's infinite, then you could get a non-compact covering space, which still has Ricci curvature bounded below. Okay, so for example, the nice consequence here is that the n-dimensional torus, this is S1 to the n, does not have a matrix with positive Ricci. Okay, so this is a very nice consequence. Yeah, any question? Yeah, so today, I want to tell you about another kind of curvature. So, there's various notions of curvature. So Ricci is like the trace of the Riemann tensor in some sense. You can go further and look at the scalar curvature, which is just a number, and it's the generalization of the Gaussian curvature in higher dimensions. Okay, so if you want to try to understand the same kind of results for that, it's much more complicated. So for scalar curvature, the situation is more complicated. Okay, in some sense, this condition, it's a tensor being positive, so bigger. So there's many conditions. Scalar curvature is just a number being positive. It's a much less strong condition. And in fact, just as a remark, if you pick any manifold and multiply by S2, you can pick this S2 to be round and very, very small, and this will have positive scalar curvature. So this was a positive scalar curvature for every y has a metric of positive scalar curvature for every y. So in particular, there's no constraints. This is a constraint in terms of fundamental group, but this example tells us that there cannot be constraints in terms of the fundamental group to having positive scalar curvature. Okay, so if you want to give constraints in terms of not having metrical positive scalar curvature, there must be something more subtle that comes into play. Okay, so that's what I want to tell you today. This first lecture. So this is the main results of this first lecture. Yeah, so this is this theorem that the torus doesn't have metric of positive Ricci curvature is due to Boris and Myers, and I want to tell you this other theorem. This is the goal for this first lecture. This is the theorem of Blossom from 1980s. So the one-dimensional torus does not meet a metric scalar curvature of positive value. Okay, so this this implies this in particular, but it's much stronger. Okay, and like in some sense, Bond Myers is it's purely Riemann. No, this is a purely Riemann geometry statement, and it's a purely Riemann geometry proof. This is a purely Riemann geometry statement, but the proof actually goes through different topics. Okay, so that's maybe the reason why it's very interesting. Yeah, so in particular, because just to give you an idea of what we'll try to go through. So, this is something about geometry of the torus. Yeah, and really we'll use some, at the end of the day, these are theorems. All these theorems I mentioned is about, we know something about the global topology of the space, like Euler characteristic or, fundamental group, and try to say something. So topology of the torus in particular. And, the way you get through, connect them is through analysis of PDEs. Okay, so, and in particular, the PDE that we think about is the Dirac equation. Okay, so maybe I guess, this first lecture is divided in 3 parts. The first part, I'll tell you a little bit about what the Dirac equation is. Okay, then the second part is about how these two, how to relate the Dirac equation with geometry. So here, by geometry, I mean Riemannian geometry. The second part of the lecture. And the third part will be like closing the going full circle and how this Dirac equation relates to topology. That's a good point. Okay. Yeah. Any question? Sorry, what time do we start exactly? So just to go over time.
Well.
Okay,
We are pretty flexible.
Okay, so that's Kate. Okay, yeah. So maybe
Well, let's aim for like 5 past 3.
5 past. Okay, great. Yes. Yeah, so maybe let me start saying a little bit, a few words about the Dirac equation. Yeah, so this is part 1. The Dirac equation. Okay, and maybe yeah, just to simplify things a little bit, I'll just talk about it in Rn, and then when we go to here, I'll tell you how to do it on a general manner. Okay. Yeah. So let me start by recalling that this is the Laplacian, and for me the Laplacian, I always pick the Laplacian with negative signs so that it's a positive operator. Positive definite. Okay.
I mean, that positive is very, I understand it, but it's
funny. Yeah, so it's the one that is positive definite as an operator. So yeah, if you put pluses, then it's a negative definite. Yeah. So yeah, so this is the most fundamental differential operator. Yeah, and Dirac was looking at this, and he was in his original paper, it's from the 1920s, 30s. He was looking for an operator that squares this. Okay, so he was motivated by studying relativistic quantum mechanics, and that led him to look for a first-order operator that squares this thing. Okay, so Dirac looked for first order. This is a second order operator. You look for a first order differential operator. D such that D squared is Laplace. Right? And we are looking for the positive definite one because this is the square of something, so you want it to be positive. Okay. Yeah, so let me just guide you through Dirac's thought process. So say D is it's a first order operator, so it will be let's say with constant coefficients. So it will be a a combination of derivatives. That's what we have to do, and then there's some AI. Okay, some AI constant. But I'm not deciding where they live yet. They live in some algebraic structure. to be decided. Okay, and I want that when I take the square of this thing with these properties, I get this thing back. Okay, so let's check the low dimensional cases to begin with to see what happens. For example, okay, if n equals 1, you just have this thing here, and then you square it. Okay, if you square it using the fact that AI is constant, so when you differentiate it, you don't get anything. This becomes AI squared. The squaring the x squares. Okay, that's it. And I want this to be the Laplacian, right? So I want this to be minus d squared in dx squared. Okay, so of course, so this tells me that I want that a1 squared is minus 1. So this I cannot do in real numbers, which is like where this thing originally worked. But if I allow complex numbers, then I can clearly do it. So I can set, a1 is I, and my Dirac operator is I. Okay, and this is the first, the one-dimensional Dirac operator. It's just derivative. We know there are many things you can do. The key point is that there is an I in front of it. Okay, now let's move one dimension backward. Things get a little more interesting. Yes, so if n equals 2, well, now my operator D is A1 dx1, A2 dx2. Okay, this is my operator that I want to square and get the Laplacian. Well, if I square this, I'm assuming that the AI are constant. But let me not assume that they commute. So what you get then is A1 squared, D squared, dx1 squared, A2 squared in D squared, dx2 squared plus A1, A2 plus A2, A1. Okay, the partial derivatives commute, so I can do this. Yeah, and again, I want this to be minus d squared in dx squared minus d squared in dx2 squared. Okay, so if you match the coefficients, you get that A1 squared equals A2 squared plus minus 1, and A1, A2 plus A2, A1. Okay, and these I cannot solve in complex numbers because, this equation in complex number forces one of A1, A2 to be 0, but then I have to square to minus 1. So I cannot do it. But Dirac's great idea is that you can solve this using 2x2 matrices. Okay, so if you set A1 equals 0, minus 1, 1, 0, and A2 would be 0, 5, 0. Then they solve the equation. And so the great insight of Dirac was moving beyond numbers and look at matrices. Okay, so and then the Dirac operator becomes this thing here. A1 1 plus A2 2 equals 0 minus 2 dx1 2. Okay, and now to do this, this doesn't this was we started with the Laplacian of functions, but now we really need to think about the Laplacian of C2 valued functions in order to do this. This is acting on valued functions. Okay, so if you want operator square to the Laplacian in these dimensions, you need to do this kind of algebraically more complicated thing of going by 2 matrices. Okay, but formally that does what you want. Okay, yeah, any question? Yeah, and you see, these are very closely related to the holomorphic and anti-holomorphic derivatives. So there's a close relation between the Dirac equation and the complex geometry in 2 dimensions. Okay. Yeah, and in general, you can keep on going. You always get, if you write, this is n dimensions, you keep on getting relations like this. So in general, we is sum of 3 in the side. This square is the Laplacian. You can only, the squared is -1. And AI, Aj, plus Aj, AI is 0 for I. Okay, so you just need some algebraic structure in which you can solve these things. Okay, this is in general, this is called a three-fold algebra. Okay, I won't go into the details of this, but let me just give you as an example, the next 2 cases, just to give you an idea of how they look like. So topology in some sense, it generalizes the complex numbers, and then the thing generated by this. Yeah, so if n equals 3, you need 3 matrices, and these are called the Pauli matrices. These are the matrices I, 0, -1, 0, I, 0, -1, 0, and 0, 1, 5, 0. Okay, let me call this sigma I. Okay, and you see, the last 2 matrices that I chose are the same that we had before, and I add a new one. Okay, and in general, you can build everything, in an inductive way. And n equals 4, you need 4 matrices now, and the first one, this become block matrices. So these are 4 by 4 matrices, and these are the matrices 2, 0, and then 0 minus sigma transpose conjugate sigma I. Okay, so there's a 2 periodic thing where once you from even dimension to odd, you just add on 1 matrix, and then when you go up, you get block matrices. So you can use the recipe to build these matrices as you go up in dimension. Okay, so I just gave you the low dimensional cases. Yeah, Dirac was, he was interested in quantum mechanics, so he really wanted these matrices here. So I gave you the low dimensional cases, but this is what Dirac wrote down, these 4 matrices here. Okay, so this transpose conjugate. Okay. So this was the first part, what the Dirac operator is in Rn. So this is just a nice, it's a nice operator that squares the Laplacian. It's first of all, a differential operator that squares the Laplacian. It's just in order to get that, you need to allow, think about functions with value in more complicated objects than just real numbers, complex numbers, and then C2 vectors, and then here, this will act on C4. Okay. And then, the next one will be C4, and then C8, and then they become bigger and bigger. Okay. Okay. Questions? Yeah, so this was the situation in Rn. And now I wanted to tell you what happens on a manifold. Okay, so on a Riemannian manifold, you can do the same thing. Yeah, and of course, because it's a manifold, you have to be careful defining things. But all the things we define, if you pick the right coordinate, they look exactly like the things we wrote here. So I want to write down this all the matrices very explicitly so that you know that it's a very concrete thing, even if I'll be a little more abstract as a. Okay, so on a Riemannian manifold.
Sorry,
Yeah.
I was a bit lost. So you explained what is the speed, this operator, but you did not talk about specific equation yet.
Oh, the Dirac equation, this is the operator. And the Dirac equation is this one. So, I guess an element in these sections is this and for this equation here. Yeah. Yeah, or other kind of equations. But yeah, the equations associated to the operator usually are called the Dirac equation.
Yeah, sure.
Yeah. Okay. Yes. Yeah, I guess I'll write it more explicitly when and I'll write down on a manifold. Okay, so this is, I want to somehow relate this to Riemannian geometry on a Riemannian manifold. So let me say on a Riemannian manifold. Okay. Yeah, so suppose we have MG. Okay, so you can do the same thing on a Riemannian manifold. So you can define. So now, on Rn, remember we first had complex value functions and then C2 valued functions, and then C2 valued functions, C4 valued functions. You can do the same on a manifold. It's just that now instead of C4 valued things, you have a bundle and sections of a bundle. Okay, so you can define S M. This is a Hermitian bundle. So if your manifold is n-dimensional, this has rank C is 2 to the floor of n divided by 2. Okay, this is where our function takes value. This is called a scalar bundle. Okay, so this is the analog of the C squared. So these things this thing really, they're called spinors, this thing that we take values in. And there is a connection coming from the Riemannian metric. And the connection takes section of this bundle and spits out 1/4. That is called the spin connection.
So here you are also assume that your manifold is spin.
Yes, so this you can always do locally. But if you want to do it globally, you need this extra assumption that Thomas was mentioning, provided and the spin. Okay, I want to go into the details. This is a purely topological assumption. So this is a global topological assumption. Right, so this is a very interesting story in itself, but I won't have time to go into it. But we'll always focus on topologically there will always be the assumption in the background that the manifold is spin. I'm not assuming. The torus, that's our main example, is spin. So it's fine. Okay, and yeah, so using this data, so locally, these are complicated, but if you're locally and try to do the right coordinates, at least at the point, this is the usual derivative, and everything is fine. Yeah, and in a similar way, you get the Dirac operator would be a section on this bundle to Dirac operator. Okay, and at every point, it looks like the operator that I wrote explicitly here. All right, on a suitable basis. Yeah, and this is a very nice equation. In particular, it's elliptic, first order, and self-adjoint. Okay, so elliptic, if you think of it, it's a very nice differential equation. First order, it only involves first order derivatives. And self-adjoint, it's like symmetric, if you think of it as an infinite dimensional matrix. Okay, so it's the nicest possible operator. And I wrote you the RM version of this, but just on a general spin manifold, Riemannian, you can have the same thing. Okay. Yes, of course. Yeah.
Your local things are not symmetric. Sorry, oh, you do the dual thingy.
Yeah. So there, well, the derivative is not symmetric. The in the x is not symmetric. It's Q symmetric.
Ah, okay.
Yeah. So yeah, that's why. Yeah. Yeah. So they're all Q symmetric. Yeah. Because of it. Yeah. Thanks. Yeah. Yeah. So but if you remember, yeah. So it's a Riemannian manifold. So you have to be careful when when there's two derivatives, you pick up curvature usually, right, on a Riemannian manifold. Yeah. So if you remember, we defined the Dirac operator because we were looking for something that squares to the Laplacian. Okay. Now, the Laplacian involves two derivatives. So, on a Riemannian manifold, usually when you have two derivatives, you have curvature terms popping out everywhere. Yeah, but the very nice thing here, somehow the miracle here, is that, yeah, we don't get what we wanted exactly, but almost. Okay, so let me tell you, this is the key result that brings in geometry to this field. Key result. So this is by Lawrence in the 60s. Yeah, so you can square the Dirac operator. Okay, and if you were on Flutter, we built it so that it becomes just the usual Laplacian. So if you want to write the usual Laplacian, so maybe let me remark here. Yeah, so maybe let me just start here. This is this you have this operator here, which is the connection going this way. And you can find the adjoint, which you can think of this as the transpose matrix of this. And this, you should think of this as minus the divergence. Okay, when you have a vector field, you can take the divergence, and this is exactly that, but at the bundle level. Yeah, so this is the usual, and you should think of this as this is the minus divergence composed with the gradient. Which is, this is the usual Laplacian in Rn. So this is just the bundle version of the Laplacian. So this is bundle version of Laplacian. Okay, if we were in flat space, this was exactly the Laplacian. And yeah, now everything here involves two derivatives, so there should be curvature terms popping out everywhere. The very nice miracle is that there's only zeroth order term. So this is S times K. That's only the scale. So the difference, we pick these two operators are designed to be second order and have the same second order part. When you take the difference, you expect a first order operator, right? But the miracle is that the first order part is not there, and we only have a zeroth order term, which only depends on the geometry of the underlying manifold. So I guess maybe, let me say, the miracle. Yes, miracles go in purple, I guess, right? Miracle. No first order terms. Okay, so these are both second order, and the second order cancel, and the first order also cancel. You just have with a zero. Okay, this is the magic. Okay, so this is the formula that really brings in the geometry into this story. Yeah, so let me tell you how this can be used. So this is the following consequence. It's a general theme that once you have a formula that looks like this, you can use it to prove very interesting things. It's called the Bochner technique. But yeah, it's a general strategy. So the corollary, suppose you have a closed manifold, MG, so this is closed. With suppose I have a metric with positive scalar curvature everywhere. Then there's no the kernel of this Dirac operator has no kernel. Okay, so the existence of these solutions to the Dirac equation. So this is Dirac equation. So the remark. So the solution is the Dirac equation, and solutions are called harmonic spinors. In the same way, harmonic functions are the kernel of the usual Laplacian. Harmonic spinors are the kernel of the Dirac equation. Oh yeah, sorry. A question?
No, I was for a moment just confused by the two essays on the board. The one for the spinor.
Yeah. Sorry, one is a big S.
curvature.
Yeah, should
And I
be.
was just like, no.
Yeah, little S, I guess. Yeah, sorry, we in this field we call everything S. So and then the spin structure here is a Math-Brack S. So not really like all the possible forms of writing down S. Yeah, sorry. Please feel free to stop me at any point. Yeah. But yeah, this is it's a very quick thing. So let me show you how it works. So proof. This is the only proof in this course actually. So proof. Yeah, so say you have a solution of this, and your section is not identically 0. Okay. So sorry, here for this is elliptic operator, so everything in the kernel is automatically smooth. You can assume it's smooth. Yeah, so then 0 is the L2 inner product between psi and the square of psi. Okay, just because this is 0. Okay, and then D, you should think of it as a symmetric matrix, so you can bring a D on the, well, sorry. Then we have that formula. So you can think of this as nabla. Well, I guess I brought it on the other side, which is the same. You can think of it as a psi. Nabla. Psi. Yes. Psi. That's over for psi. Right? Just plug in that formula in here. Yeah, and then nabla star is the adjoint, so I can bring it from the other side. So this is nabla star. And the two inner products. Yeah, but this term, it's an integral of something positive, right? Because this is just a constant at every point, and it's positive by assumption, because so this term is positive. Okay, so this is positive. Okay, so this is actually strictly positive. And this is the inner product of something with itself, so it's not negative. It's bigger from 0. Okay, and we got our contradiction because we say the 0 is strictly bigger than 0. Okay. Yeah, to be more precise, this is the integral of S divided by 4. No. This is a positive constant, so this is. Okay.
Sorry.
Yeah.
You didn't assume that it's constant, right?
No, I'm just assuming that it's positive here.
Yeah.
And this is not 0, not ever 0. So yeah, so this is the just integration by parts. That's what all we're doing here. Okay, so this allows us to recap a little bit what we're trying to do. This allows us to relate this PDE, so being able to solve this differential equation, to the geometry of the manifold. Okay, and now to finish everything, we need to somehow relate solvability of this equation to the topology of the manifold. Okay, so this is the final part of this first talk, so relation with topology. Okay, so in this situation, maybe let me focus in, even or not, if you remember, there's a slightly different theory, but let me say, for example, say n even.
Wait, can I ask a question?
Yes, sir.
So what's the Fresnel index of D?
Yeah, that's what I'm talking about.
Oh,
Yeah,
sorry.
Yeah. Mhm. Yeah. Sorry, spoilers. Yes. Yeah, so there is a, if you remember our matrices, n equals 2, our matrices that we were interested in had this form, right? So A1 was this, and A2 was this. Okay, so they have this block structure. They have zeros on the block, on the diagonal blocks, and non-interesting matrices on the other blocks, right? So this implies that, somehow if you split, you can split your space in two pieces, and this matrix interchanges the two pieces because of the shape of the blocks. Okay, so you can, our bundle S over your manifold M splits as S plus, S is S plus, direct sum S minus. And the Dirac operator, you can write it as 0, D minus D plus, where you have sections of S plus, D plus, S minus. Okay, in this case, it would be like 0. We will be x1 plus I in x2. X1 plus I. Okay, so D plus will be, this homomorphic derivative, and this one will be, this in D in this Z bar, and this in this Z, or vice versa, for mine. Yeah, I was a bit confused. Yes, so this is, in even dimension, our Dirac operator splits into two pieces. Yeah, and the key property that Thomas mentioned is like if you have a M compact, if you have a compact manifold, because our operator is elliptic, then it's Fresnel. So in particular, so if you have a compact manifold, and compact is implied by implicitly that the dimension of pair D plus is finite. Okay, so the solutions, the kernel of this operator is finite dimensional, and the dimension of the co-kernel of D plus. So the image module, the range module of the image, which is the same as the dimension of the kernel of D minus, which is also finite. Okay, so there's some kind of finiteness properties for the, the kernel of this operator. It's a differential operator, so who knows? But it turns out to be always finite dimensional. So the space of harmonic spinors on a compact manifold is always finite dimensional. And because they're finite, you can set the index of D plus. This is the dimension of kernel of D plus minus the dimension of kernel of D plus, and this is an integer. Okay, so this means, in more technical words, so this means that D plus is Fresnel, and this is the Fresnel matrix. Okay. Yeah, and this is helpful because in general, these quantities, the dimension of the kernels, are not topological invariant. So if you change the metric, they change. The very great thing is that this index is independent of the metric. Okay, so it's a purely topological invariant. So this is independent of metric. Okay, so this difference between dimensional kernel and kernel doesn't change if you change the metric, while the two numbers change, but the difference doesn't change. Okay, and this is the final point. So maybe let me keep that there. And I'll put this here. This is the theorem of Ati and Singer, so theorem and Singer in the 60s. Okay, so if you have an G closed manifold, okay, this was the underlying assumption that allows us to write the Dirac operator in the first place. It's higher. Then there is a formula to compute index of B plus. Okay, so in general, to compute this index, you need to solve some PDEs and then take the difference of the dimensions you find. But yeah, the miracle is that this is a topological invariant. So there's hope they can be able to write it just purely in terms of the topology, and that's actually what they do. Purely in terms of the topology of M and its tangent model. Okay, so if you're familiar with them, then these are the Pontiac classes. PM is the H4. Okay, so these are purely topological invariants, no metric involved. If you can compute this, then you can say something about the index. Okay. Yeah, and if you put this together with this, so if S bigger than 0, okay, then there's no solutions. Okay, so both these two are 0, so the index has to be 0. So the formula has to give you 0. This formula that I will write gives you 0.
Wait, maybe I missed one point. So you have D plus and D minus,
Mhm.
and I guess that the index of D is somehow the index of D plus.
No, well, the issue here is that D is self-adjoint, so the index is 0.
Okay.
So to do something interesting, you need to break the thing into two pieces.
Yeah.
Yeah. And these are adjoint to each other. So the index of this is minus. The index of this.
So that's
Mhm.
okay.
Yeah, but the kernel of this is the kernel of D plus and the kernel of D minus. So, so if you want,
No.
so this is the same as D plus and D minus both have a 0 kernel. Yeah. Yeah. So yeah, I won't write down the formula. You get huge numbers, like 1 over number with lots of digits and crazy numbers. Yeah, there's actually rational numbers coming. Yeah, very big rational numbers coming up. But yeah, let me just give you an example. So if you have, the first example in which you can do something like this, which is interesting, is the so-called K3 surface. And this is, it's a algebraic hypersurface. And just an example. This is 0.4 plus onto the zeros of this quartic polynomial inside CP3. And these are smooth for manifold. Yeah, and this formula, if you compute the formula that Atiyah and Singer give you, you don't get 0. Okay, you get -2, something like that. So yeah, so no metrics. There's no metrics on positive scalar curvature on this specific for manifold. And this is, by the way, this example is particularly interesting because Yao showed that it emits a Ricci flat metric. So, so you have a metric which is Ricci flat, but there's no metric which has positive scalar curvature. So it's a very interesting example. Yes.
When you say this formula gives you 0, you mean the index?
Yeah, the index formula here.
Okay,
yeah.
I don't understand what this refers to.
Yeah, the Atiyah formula. Yeah, sorry, I will not write it down, but there's a formula. And yeah.
So the index of P plus is 0, and then you can compute the index of P plus for a K3 surface, and it turns out to be something else.
Yes. So it doesn't have a metric of positive scalar curvature. Yeah, that's the logic. Yeah, thanks. yeah, so this is a very interesting example where you can do it. So maybe one thing that I want to tell you about the formula is that it's it's a polynomial in these Pontryagin classes with no. So if the Pontryagin classes are all 0, then the formula gives you 0. Okay, so in particular, this strategy doesn't work for the topos. So that's our main goal at the beginning. So maybe so the strategy works if your bundle is complicated enough, if your manifold is complicated enough. The torus somehow is too simple for this to work. So the issue of applying this strategy right away is that the tangent bundle of the torus is trivial. So in particular, all these Pontryagin classes are also trivial, and the formula gives you 0. So formula gives index of the class equals 0, so we don't have no obstructions. Positive scalar curvature from just this strategy. Okay, so it's a very nice thing, but it doesn't work for our original goal. But it took some few years, more years too.
In the case of the so if you do the computation with flat metric.
No, so the index is is a topological formula, and just take in as input the Pontryagin classes, and those are all 0 because the tangent bundle is trivial.
Yeah, yes, but I mean, in that case, you could also, if you don't know the ideas in the formula.
Oh yeah, you can also yeah. In that case, you can also just compute the thing. You can just the spinors, you can just compute them with that match. I'll go back to this in the next lecture actually. Yeah, thanks. So maybe let me tell you, I guess in the last 10 minutes, let me give you a sketch of what Gromov and Lawson do to go, they use a similar strategy, so somehow relate geometry with the existence of harmonic spinors and the harmonic spinors to topology, but they need to do something more refined just because this thing will not work for the torus. Okay, so how did they manage to go beyond this? Yes, so I guess it is a very nice general idea. So in these situations, we've been only looking at a single operator. Right? So we have one Dirac operator, and we've been looking at how it behaves. But yeah, there's this nice thing that I tell you now that you can really, there's not really just one Dirac operator, there's a lot of them. So if you look at all of them, you can see some extra structure that will help you solve the problem. So this is Gromov-Lawson. Let me see. Okay, so this will bring everything together, 3 parts on the top. So the idea is that we can always we have our given Dirac operator that just the metric and the spin structure gives a Dirac operator, but really you can twist it with other kind of geometric objects. In particular, what you can do is like twist the Dirac operator on M. And what you can do is like you twist it by a flat complex line bundle. L. Okay, so flat complex line bundles on your manifold M, these are in correspondence with the holonomy. So a flat line bundle is determined by its holonomy around loops. So the holonomy, this is the same as H1 of M, coefficients in the algebra over H1 of M. Okay, these are called the. Let's say this is the torus of flat. In the case of the torus, maybe this is the case we are interested in, well, this turns out to be another torus. So this is the torus of flat connections.
H2, no, maybe?
No, because that's the topology of the bundle.
Okay.
But the bundle will be topologically trivial because it's flat.
Okay, sorry.
And then here flat means I think both of the bundle and the connection. So
Okay.
yeah. So
sorry,
bundle, composite bundle with connection. With flat connection.
Okay, yeah.
So this is my torus Tn. Yeah, and this is a torus, and a new torus, another torus. So the torus of flat connections on my torus is another torus. In general, if you have a manifold of B1 equals K, then you get a K-dimensional torus. Okay. Yeah, plus other components maybe.
Sorry, I have another question.
Yes.
We're trying to investigate the n-dimensional actual torus.
Yes.
N is even, or do we not care, or you only treat the
No,
even
yeah,
case?
if you have a metric of positive charge curvature on the torus, then you get it also on S1 times the torus. So you can just, if you solve it for n even, then you solve it for every n. Yeah.
I see.
Yeah, that's a good point. Yeah. Yeah.
Mhm.
Yeah. So we'll focus just on n even for simplicity. Yeah, the story is very different. So I kind of, yeah, it's okay. Another torus. Okay, and with this, if you look a little bit into the theory, we had our Dirac operator, and you can twist the Dirac operator. So you can look at twist the Dirac operator. I'll call it maybe DL from section of S. This is our original scalar bundle. I tensor with this flatline bundle to S. Okay, and the fact that L is flat, okay, L is equal with the square metric implies that the linear of its formula still holds. Okay, so the square of the Dirac operator is the same as the Laplacian plus the scalar curvature. In general, if you twist it with a more complicated connection, you get an extra curvature term depending on the curvature of your path. Okay, so yes, DL squared, nabla L plus S squared 4. Okay, in general, you get an extra curvature term.
But then that suggests that, I mean, we don't care about the sign of the remaining term, no? So you can just take maybe.
Yeah, depending on the situation, but yeah, I guess that in the torus, I don't think you can. Yeah. Depends on the situation that you can use something like that. Yeah. So. Yes. Yeah, and each of these operator, the index formula, each of these operators is still trivial, but now we have a lot of them, so we can look at the whole family. So each of these operator is trivial, meaning that the index of the L plus is again 0. Okay, so you cannot use these to, the strategy works. If one of these operators work, then, having index on 0, you can finish, but each of these doesn't work. The idea is to look at the whole family of them. So it's a whole family parameterized by a new torus. Okay. But the family of operators, the L, where L belongs to these flat connections, flat bundles, is topologically useful. Okay, so I'll mention a little later in the second talk what exactly means by topologically interesting. But yeah, so let me just finish this talk by mentioning the Singer for families. Right, so for the single operator, you don't get anything interesting on the torus. If you look at all of them, this interesting topology detected by the cohomology ring of the things. Okay, and the torus has a very interesting cohomology ring. You have cup products which are not trivial, as many as you want, And so from this non-triviality, because the topology here is non-trivial, Gromov and Lozo were able to conclude that this family is non-trivial, and so you cannot have, you must have, you cannot have positive scalar curvature. Okay, I'll make this a little clearer in the next lecture. What I mean, yeah. But yeah, at the end of the day, it's everything boils down to the cohomology of the torus rather than its tangent bundle, which is trivial.
Well, Francesco, I am very excited about part 2.
Okay.
So I think I speak for everyone.
Yeah, thank you very much. Yes, well, thank you for the cake. Yeah, so I maybe, yeah, I guess maybe I'll start discussing a little more in detail the thing that I said very vaguely, that this you can detect the non-triviality of this family using topology. But yeah, so I'll go towards application to geometry in 3 dimensions. So I'll, I guess before I was talking more about even dimensional things, but now I'll switch back to more three manifolds, I guess. Yeah, by the way, the first part of the lecture was based on, the first part of the Gromov-Lawson paper. But yeah, so yeah, let me just review a little bit what we did. So yeah, so I guess we have our manifold M, G, okay, our spin manifold, and we have the Dirac operator, but we can also twist it, right? So before I twisted it with a flat connection, but you can twist it with any connection in general. So let me say, so L, this is a line bundle. Maybe let me say topologically integral. Line bundle, connection. This will be my notation for the connection on the line bundle. Yeah, so we from here you get the twisted Dirac operator that earlier I didn't know was stands for L itself. But yeah, I think for my perspective, I usually like to think of this, topologically, this is exactly the same bundle. It just has a different connection. So I just fix the bundle and change the connection. So maybe this answers your question before. So think of UB from itself. This is a new connection on my bundle S. Okay, and this, if you get a connection with this this construction, so answered by a line bundle, this is what is called a spin C connection in technical terms. It is called spin C. Okay, so usually I'll think of, if you just pick the usual connection, that's called a spin connection, we can twist it with this one connection. I get this new interesting connection on this bundle, and each of these has a Dirac operator. Okay, so now, in the setup as before, if let's say you have Y at 3 manifold, then you get this family of Dirac operators, which you parameterize by torus of flat connection on Y. So maybe let me call this TY. This is the torus. This is flat torus flat one connections. Okay, and this has dimension equals B1. Okay, so it's the first cohomology of Y modulo a lattice. So whenever you have a 3 manifold, you get a B1 dimensional family of operators. Okay, each of these, these are all self-adjoint, so these are not interesting because the index is always 0. But yeah, this family turns out to be very interesting. So let me tell you a little bit about this family of Dirac operators. Okay, this is the family of Dirac operators we'll think about in this lecture. So don't just get one, you get a whole big dimensional family of this. Okay, so this is a theorem. This is, I'm gonna have less in there. So in general, these are what we call Fredholm operators, and they are set adjoint. And these families of these kind of operators are classified, parameterized by P. So here I'm in a much more general setup. I have some kind of space of Fredholm operators self-adjoint, and here I have some space that parameterizes called P. These are classified by some homotopy class of maps from the space P to U infinity. Okay, so yeah, so this you can think of this is kind of really there's some space classifying Fredholm operators. So these are called self-adjoint. There's some suitable space of self-adjoint Fredholm operators, and turns out to be homotopy equivalent to U infinity, which is the union of all the unitary groups UN. Okay, so the space of all these operators has some very interesting topology. It's homotopy equivalent to U infinity. So it has a very interesting topology. If you look at the space of all these operators, maybe this, if you maybe this is something you see more familiar with, pi1 of U infinity, this is Z, and this corresponds to spectral flow in the third field. So this so spectral flow really is something looking about one parameter families of these operators, and that's classified by the spectral flow. And this corresponds to. Okay, so there's a general result telling you there's some space that's classified as homotopy class of maps in that space, classify all these operators. And Atiyah and Singer also tell you this specific element, this specific family, what it corresponds to. Okay, so so I guess this is another theorem. Again, it's here. For a three-manifold, this family would be in this torus of the function y is determined by the triple cup product. Okay, and this is just a map, cup y3 from y is equal to z. Triple cup product means here you can take three cup products of things and evaluate on the fundamental class, and this gives you the objects. That's for 1, 2, 3. Let's do it for 1, cup for 2, for 3. Evaluate in the fundamental class. Okay, in particular, in a suitable sense that I want, maybe I'll just in words, this corresponds to K1, so odd K theory of your space. And if you take the Chern character of that, you get some homology class, which corresponds to this here. Okay, so in particular, if this triple cup, so this only depends on the topology of your cohomology ring of your underlying space. If this is non-trivial, then you get a non-trivial family of operators. So that's maybe the way we'll use it. So if this operation in cohomology of your underlying space is non-trivial, then this family of operators is non-trivial. Okay. Yes, and there's a higher dimensional version of this where this cohomology class comes in play, and also the Pontryagin class is in 3 dimensions. There's no Pontryagin class because the first one lives in H4, so it's only triple cup product. Yes, so this in some sense, this is saying that, for example, for the torus, the torus, this, if you take the product of the three generators, then you get the top class. So this is non-trivial. So for y equals t, this is t. Okay, and this is how you show that that cannot be a metric of positive scalar curvature. Otherwise, this family would be trivial. Okay.
So can I ask you something? So I'm quite familiar with, well, a version of this where you don't have self-adjoint operators, but you just have Fredholm operators.
Oh yeah,
And
yeah.
then, well, in the normal Fredholm operators, and then you have K-theory, and this is K1.
K1.
So how do you think of a K1 class?
That's a good question. Yeah, I don't know how to think of a K1 class.
Okay.
The way I would think is just take the Chern character and you get the odd-dimensional homology class. I guess that's how you usually think of these classes. Yeah, yeah. I don't know how to think directly of a K1 class. Yeah, that's a good question. Yeah. But you go through like looping or de-looping to another class if you want.
Yeah, sure.
Yeah.
Okay.
Yeah.
Francesco,
Yeah.
can I say why positive scalar curvature gives triviality?
Oh yeah, maybe let me say. So the key point. So if you have a family of isomorphisms, then that map is homotopically trivial. So for a family, let me say, if you have a family of maps, EP, where P is in a quantizing space, then the corresponding map from P to infinity is homotopically trivial. And this is not obvious. This is also a theorem of Thiel and Singer. So if you have a family of isomorphisms, then they're also trivial. And having positive scalar curvature means that all of these will be isomorphisms. So they don't have kernel and they're self-adjoint. So if S bigger than 0, then the Ty is a family of isomorphisms.
I'm confused.
Hmm?
I'm confused. So
Yeah.
maybe, what do you mean with an isomorphism? Something in UN is an isomorphism. So
Well, these are operators. These operators from some hits, L21 to L2, maybe it's an isomorphism. So here, the thing I'm not telling you is how to go from a family here to a homotopic class here, maybe.
yes, that I think I understand.
Yeah. And if each of these operators,
These are all isomorphisms, always.
no, because if there's kernel, then there might not be, the Dirac operator. These are not Dirac operators. So if there's kernel, then it's not an isomorphism. And there is isomorphism exactly when there is no kernel.
Okay, so maybe can you explain one more time how you get to U infinity?
Well, that's not, that's the hard part of this whole story. Yeah. But yeah, in general, you have a family of operators and you get some homotopic class here. Yeah, but the operators are not assumed to be isomorphisms. They can be any family of operators. Yeah.
So then in this key point, it's for a family TP of isomorphisms.
No, for a family of any operators of operators. The corresponding class is homotopically trivial. If you have positive character, you have a family of homotopically trivial maps. So this map is trivial, but at the single computed in terms of the triple cup product. So if the triple cup product is not trivial, this cannot be trivial. And that's the final contradiction. Yeah. So you cannot have, essentially when this triple cup product is non-trivial, you cannot have, the family of operator is not a family of isomorphisms. It's a family of operators, but it's not a family of isomorphisms.
No, but then I'm
Okay,
confused
maybe
because you
I
wrote
can-
operators, but I mean, you do mean as, no, I don't understand the reason. That was my comment.
Yeah.
The isomorphism. Yes, right.
Sorry, yeah, sorry.
That's what I meant.
Yeah, I was also confused.
Yeah.
Sorry. So if you have an isomorphism, then this one topic can share. Yeah, sorry. Sorry, I made a little bit of, is the logic clear? Yes. No, maybe you're still not happy with.
I think maybe I want to know something here which you don't want to tell, so maybe I'll ask you later.
Yeah, I guess maybe the thing I'm really hiding is how from a family of operators you get a homotopy class of maps, I guess.
Yeah, but I can imagine that this is exactly somehow keeping track of a family going from the kernel to the co-kernel or something.
Yeah, that works in the not self-adjoint case, and it has self-adjoint case. You need to take loops of things. So yeah.
Okay.
Yeah. Sorry for the confusion. Yeah.
Okay.
So maybe So this is the thing that I explained before. This is the Lickner-Lorentz formula implies that if you have a family of isomorph, if positive scalar curvature, then it's a family of isomorphism. Then the homotopy class of this map is trivial. The Atiyah Singer tells me that it cannot be trivial. The final law. Okay, great. Yes. Okay, so this tells me in particular, so I guess consequence, maybe to sum up, if cap y3 is not 0, okay, so if this map is not identically 0, then this is not a family of isomorphism. Y is not a family. Okay, so this is the consequence. So maybe the question is then, can you say something? So this means that at some point, for some B in this torus, there is some kernel, right? So you can ask yourself, can you say something more detailed about this? Okay, so question for given y g, can one say something more precise? Okay, so not everywhere you have an isomorphism. Can you say a little bit maybe about the locus where it failed to be an isomorphism? Okay, let me just give you an example. I guess this is what Gabriele was mentioning before. Like in the case of the torus with the flat metric, you can do it very explicitly. So example. Okay, so P3 with the G flat metric. Okay, then I guess in this situation for DB squared is star number B. So here the scalar curvature is 0, so this is flat. This implies that harmonic spinors, which means that DB side 0 are parallel. Okay, so covariantly constant. And my D and my delta nabla are superly similar, but this is a nabla. Okay, so they're determined by the value. So this is the same integration by part argument we had before. So they have a parallel and harmonic spinor is determined by its value at a point. Right? So you can do computation very concretely. So they are determined by value. Okay, so and from here you can do all the computations and you can show that the kernel of DB, okay, this is C2 if it is a trivial connection, and 0 if not trivial. Okay, so there's a three-dimensional torus of flat connections, and there is exactly one point where there is a kernel. Okay, something like this. That is my torus of flat connection. So I denoted it by sorry, this I denote by T3. This is the torus. This is the torus of flat connections, and there is exactly one point in the middle where there's kernel. And everywhere else, there's no kernel. So this family fails to be an isomorphism is exactly at one point. Only one point is not an isomorphism. Okay, not iso exactly. Okay, everywhere else, this operator is an isomorphism except at this single point, which is special. Okay, so to say, I think this is, to say something a little more robust, these are very non-generic things. So if you perturb a little bit, the picture changes. So let me show you a slightly more robust thing to say. Yeah, so maybe the geometric picture is the following. Okay, so we have this space of operators, so space of self-adjoint problem operators. Okay, let me use my space. Okay, and then the operators where there is, you should think of it just, symmetric, Hermitian matrices or something like that. So the kernel is where the terminal is 0, so it's a hypersurface. So there's a codimension 1 hypersurface. Where kernel is equal to 0. Okay. Yeah, and the hypersurface in general is singular, so there are some singularities. The singularities are in codimension at most 4. So these singularities.
At least.
Yeah, at least 4. So in codimension bigger than 4. Okay, and this corresponds where the kernel of T is at least 2. Okay, so here, this hypersurface where there is kernel, generically you have one-dimensional kernel, and that's a hypersurface. And then when you have bigger kernel, you're the singular locus like this. Okay, so now if I map my 3 torus here, you should expect that generically you don't hit the singularities, right? Because this is a codimension 4, my torus is 3-dimensional. So my torus should miss the orange part. Okay. Yeah, and the locus where there is kernel should be a hypersurface inside there. Okay, and that you can do explicitly if you perturb a little bit.
Right. Can you say again why this kernel was C2 and?
Oh yeah, so there's a trivial connection.
Mhm.
This is correspond to the trivial connection. So if you pick a point and you parallel transport, and every value you start with, you close it up.
Yes.
From the other one, there's holonomy. So when you go around twisted, so everything doesn't close up. So once you have a holonomy, there's no kernel.
Okay.
Yeah.
Mhm.
Yeah. So if you perturb the picture a little bit, for delta equal to 0, we can look at the family d minus delta. Okay, so the kernel of this is some kind of eigenvalue equation, so db psi equals psi. And kernel of d minus delta becomes a small sphere. Okay, so the picture now is the following. So this again, the kind of computation that you can do very explicitly here because everything is very explicit. So these were my original points. And now this is sorry, here the locus where this is. Okay, so this is the locus. It becomes a little smooth sphere. Okay, so this single point here, which is the Dirac operator itself, if you look at this small eigenvalue equation, it becomes a little sphere around here. So here is where no. Okay. Which matches up with this picture because the locus where you don't have kernel is a hypersurface inside your space. So this turns out to be this little hypersurface in this space.
Sorry, delta is in this story what? It's a
Small real number. Yeah, for maybe I guess small real number. Yeah. Okay. Yeah. So this, the locus where you can think of it, the locus where dB has eigenvalue delta is this little sphere. Okay, this is delta is eigenvalue. Okay, so you got this little nice sphere. Okay, this is another very concrete computation you can do once you think about this thing I said briefly. Okay, so maybe the question that I want to address is just focusing on the case of the torus. So what can you say? So, but see, here I was really using the flat metric, right? So this equation only holds for the flat metric. So everything here was for the fermi metric. What can you say for general? Let's focus. Okay, I'll talk about the torus for the whole lecture, but a general metric.
Also, Francesco, because maybe I was expecting that the orange locus would be a non-trivial homology class or something to indicate that the family of operators.
Oh no, that's I don't think that doesn't come up in the picture. Yeah.
Okay.
Yeah. I think what happens is that so what happens is the triple cup product will restrict to a trivial element in both, in the components that you can say. But the homology class of the thing is not determined. So this is the question I want to answer a little bit. So if you have your Dirac, so I guess maybe the question is like, let's say okay, so maybe what's a shape of A, the locus where of B such that B has kernel inside the torus of okay, so if you pick a generic metric, what does this sphere look like? Is it something else? Is it topologically trivial? Is what kind of object do you get? Okay, and here again, here behind the scenes, I will not be looking at this operator itself, but at a time, a small perturbation. Okay, just to get this kind of more generic picture rather than this very degenerate picture. So then you can say something more. So you can actually say something.
Francesco, can I bother you again?
Yeah, sure.
Kind of the same question.
Yeah.
Okay, let's see. Because you said, okay, the family of operators is non-trivial. So it represents some kind of non-trivial homology class of operators. But you're not seeing this via some kind of homological pairing with this hypersurface, because some of the pairing here seems kind of trivial, right?
Yeah, so the homological pairing with the hypersurface is the spectral flow. And in this family, don't have spectral flow, so the loops don't pair with this. If you have some kind of parallel operator in spectral flow, then this would be a separated hypersurface or something. Yeah, so that you can see. Yeah. But yeah, I mean, this is all the cases I think about. I'm only looking at the situation with all spectral flow. Yeah.
And okay, I think I'm happy. So.
Okay, yeah. So yeah, I guess it's a good question. What can you see out of that hypersurface? Yeah. But yeah, in general, yeah, tells you the homology class is the spectral flow. Yeah, actually that's true. Yeah, sorry. Okay, yeah. So this is the kind of question. I think so. Let me just remind you that the Atiyah-Singer theorem that we mentioned means that because torus has non-trivial triple cup product, this locus is always non-empty for every metric. Okay, just because otherwise we will have a family of isomorphisms, and then that cannot happen. But yeah, in general, if you pick a random metric, it might be arbitrarily complicated, and who knows what this thing looks like. Okay, so I guess maybe that's what I want to go to is like for general metric, you cannot say anything about this. You just know that it's non-empty and it's a hypersurface. Okay, so yeah.
Maybe for Borden to this one, right? It's no Borden for sure.
Yeah, I guess in the
because you can take a path to this metric to your.
Yeah. You can say the homology class of the hypersurface will be trivial, and these kind of things you can say, yeah. But yeah, I want to say something more robust, let's say, more geometric. Yeah. So and for this, you have to go, put some constraint. we're gonna go to a generic metric and say what this thing would look like. Yeah, so that's where the spectral geometry comes in. So the condition that I would want to impose are some kind of spectral conditions. Let me review a little bit and state the main theorem, and tell you a little bit the motivation behind this more general state. Okay, so let me just recall maybe. So we have the round complex. So we have differentials here. Is the round complex, and if you have a metric, so this only depends on the manifold itself. But once you have a metric, you get the adjoints here at the time. These are these stuff. We have enough products. And yeah, so from here, the key operator is the Hodge-Lap function. Okay, and this is defined to be plus squared. Okay, and on zero forms, this is the usual Laplacian, the one that we started with from Dirac in Rn. But this is a Laplacian on differential, the natural Laplacian to study on differential forms. Yeah, the key result here is the Hodge theorem. Okay, so I'll only look at one forms, but you can do it for any forms. So the one forms they compose as a direct sum of exact forms plus the kernel of the Laplacian, direct sum for exact forms. Okay, so these are called exact. These are called coexact, and these are called harmonic. Okay, and these are isomorphic to H1 of the manifold. Okay, so this is a very natural decomposition of differential forms once you have a metric on your space. Sorry, what time do we start?
Started a quarter to.
Okay. Good. Okay. Yeah. So this I'll look at this decomposition, but I'll look at a little more fancy. In particular, this decomposition is preserved by the Laplacian, and the Laplacian, you should think of it as some kind of infinite dimensional matrix, so symmetric matrix. So Laplacian acts on coexact forms, and is diagonalizable. In the two. And I denote the spectrum by this. These are the eigenvalues of the Laplacian. And this is the first eigenvalue is positive because the kernel is all taken here. So there's no kernel here, so there's no zero as an eigenvalue. Okay, but it's positive. And the key quantity that I want to think about is the key quantity. Okay, so maybe you're more familiar with the Laplacian on functions, and it turns out it's the same as the Laplacian on exact forms, and that you can think of it as the frequencies at which your manifold thought as a drum vibrates. Okay, this you can think of the physical meaning of this is like if you think of your manifold as some kind of magnetic cavity, these are the frequencies at which the magnetic field can oscillate. Okay, that's the meaning of this quantity. Yeah, so let me, so this is the quantity I'm interested in, and let me give you the definition. Riemannian three-manifold is spectrally large Yes, with this first eigenvalue is at least as big as the infinimo of the Ricci curvature. Okay, so if Ricci, sorry, big is strictly bigger. Ricci is bigger equal than minus k, and lambda 1 star is bigger than k, then spectrally. Okay, so it's a general thing that one would like in general. This somehow is a measure of how complicated your space is, and this is a quantity that tends to be very small in general. So a meaningful thing to ask is how it's to ask it for it to be big. Okay, so this is a kind of general definition that fits well in the realm of spectral geometry, for example. I want my eigenvalue to be big compared to some other quantity in your space. Okay, so the basic example is actually the flat torus.
Science correct? Maybe. I'm not.
I think so. Yeah. Yeah.
But should I be thinking of like negatively Ricci curve things or positively?
Yeah, I'll think about negative things with some negative curvature. Yeah. So because that's a good point. If the Ricci curvature is always positive, then the scalar curvature is positive, and the torus that's not the case.
Okay,
Yeah. So yeah, thanks. So I want some negativity in the Ricci curvature, right? So yeah, maybe I should say that. I guess the story went on further. So in three manifolds, positive scalar curvature is a very, very restrictive assumption topologically. It's like your quotient of the sphere with some handles attached. So one handle is attached. So it's a very, if you like three manifold with positive scalar curvature, you like very few manifolds. Yeah. So we would like to look at a much broader case. So we need to allow some kind of negativity in the curvature to do things. And this is so for example, C3 with the flat metric is spectrally large. Okay, because lambda 1 star, well, this is a positive number, which is which. Okay. So this is the example we were thinking about before is a spectrally large manifold, the flat torus. And all these things are actually continuous in the metric in the C2 topology. So also true, also spectrally large. G is spectrally closed, C2 closed. G flat. That's like you're relatively close to both these quantity change continuously, so that is inequality was still. In general, unclear to say what's the space of spectrally flat matrix, spectrally large matrix on the torus. That's a very hard question to even say anything basic about that, right? So it's a very, this is a local condition, but this, you just saw some people do about PDEs, so this is a very complicated thing to check in practice.
But if I take like something flat and I make like, or I take something and I take like a local thing where I'm just like bumping up the curvature or like making it small. Can you say something about the smallest eigenvalue? Like what that does to it?
Yeah, I think at some point, if you deform too much, it won't be spectrally large anymore, I think. Yeah.
Okay, so these are sort of things.
Yeah. So
yeah,
that's the picture to have, but it's unclear how. If I give a specific metric or what's the shape of all these metrics, that's very, very hard.
And can you do some sort of surgery adapted to the spectral large?
Yeah, you can do something like that. It's in general very hard to control. Get reasonable. It's hard to give very bad bounds on the lambda 1 star. It's very hard to give reasonably good bounds. So once doing surgery, you can give a lower bound, but it's hard to tell if this still holds.
Oh,
yeah. So that's a very interesting question, actually. In general, I mean, I'll just say maybe in general. Unclear. What? Okay. what are the spectrally large metrics on the torus when these eigenvalues. Okay, but yeah, this is the main theorem that I want to tell you today. Suppose you have the three torus and G, which is spectrally large. Then the locus K of these flat connections where VP has kernel. This is inside the torus of flat connection. But also it's a locus in these other torus. You know, before it was just a small round sphere. It's always, you know, after small perturbations, is diffeomorphic to S2. Okay, so once you put this assumption, which is somehow global in nature, on the metric, you still get a sphere. Okay, I don't know what the shape of the sphere is, but you know, before it was a nice round sphere. And in this situation, you can still conclude that it's a sphere topologically. But yeah, you might have nothing. I'm not sure what the shape exactly is. It's a sphere. Yeah. Okay. Yeah, so still you can conclude something about where the Dirac operator is, just the topology of the. Okay, in general, you know, if you look at non-spectral large, you know, this thing you might get higher Gino surfaces which are embedded in a weird way and stuff, right? But yeah, so this is the once you have this assumption that this first eigenvalue is big enough compared to the rich curvature, you get this this constraint on the shape of this locus where you fail to be an isomorph.
And how flexible is this? Because I mean, could you like for any embedded surface with any nothing, could you get that as the?
Oh, that's a very good question. Seems very, yeah, I don't know. Yeah, that's a very good question. Yeah, I don't know how. Yeah, I guess spheres in T3 are never unknowed. Always unknowed. So this thing always bounds a ball, but once you have higher Gino surfaces, they might be non-isotopic and stuff. So that's a good question. Yeah.
Is the space of spectrally large metrics connected?
Unknown, I guess. Yeah, as far as I know, it's unknown. Yeah. Yeah, so it might be some other component and it's still a sphere or something. Yeah.
That would be very interesting, right?
Yeah.
Here, otherwise it feels a bit like a sort of a perturbative maybe argument.
No, the argument is non-perturbative at all. So
okay.
yeah. So I don't know if I guess it's a good question if you can prove this with a perturbative argument. Yeah, that's I don't know yet. Yeah, but it depends. Yeah, whenever, I don't know how many components this space of spectral large metric is. Then any component has.
I'm not trying to dish your here.
Oh no! I was just to clarify. Okay. Questions? Yeah. So. Yeah, so I guess the last 15 minutes, I want to give you a sketch of the ideas that go into the proof of this. Yeah, so why is this thing a sphere, I guess, the question, always. Yeah, so I guess maybe the thing, the main theme, maybe, so the new ingredient, yes, I think index theory, the Matthias Singer doesn't get you further than this is non-empty. But all the things I've told you about so far are about linear operators. So I look at the Dirac operator as linear. Well, you know, also the statement is about linear operators. This is eigenvalues, so that's a linear equation. But everything was about linear equations. So we only have about linear so far. But the proof of this uses nonlinear things. Okay, so in particular, the nonlinear PDEs that come into play, and you know the reason why I stated this still only for three manifolds and not in every dimension, is that this PDEs only exist in three dimensions. Yeah. So, yeah. Yeah, so these are the cyber-Witten equations. Yeah, so these are equations for a pair the psi, where the first thing is a spin C connection. Okay, this is one of these connections on my bundle S obtained by twisting by a connection on the line bundle. And this is a spin. Okay, so this is a section my spinor bundle. Okay. Yeah, the equations, I'll write them down. I won't explain too much what they are. So the first equation we've been talking about is all the time. So it's just a Dirac equation for this, so size harmonic for this. Yeah, and the second equation. So here, but I guess so far we've only been thinking the case where B is comes from a flat connection. Here I'm allowing B to be not necessarily coming from a flat connection. So it's a much more general thing. And in the Lichner-Horowitz formula, you pick up a curvature term. The curvature term pops up. Okay? So it's a much more general thing. And then there's a nonlinearity coming here, which is quadratic in nature, so it's not too bad. Okay, I won't explain too much. This is the curvature of your connection that you twist with, and this is some kind of quadratic nonlinear. Okay, and this is the curvature of the connection on the line bundle that B comes from. Okay, so it's a kind of some kind of generalization. You see that there's the Dirac operator that we've been talking about for the past hour and more. But yeah, that you also get this extra equation that somehow is nonlinear. Okay.
So I guess that this is a nonlinear Fredholm problem.
Yeah, there's all the symmetries of the equation. Once you quotient by that, then it's a nonlinear Fredholm problem. Yeah.
What's the index of that thing?
Oh, it's zero.
It is zero.
Yeah, it's in 3D, I guess. Yeah, everything. Yeah, the index is a quadrant, so it's zero. Yeah.
Okay.
Yeah. Yeah. Yes, I guess the power of this thing is that you can use this equation to cook up a much more powerful topological invariant than the ones we thought about. So far we talked about everything boiled down, all the story about linear operators boiled down to contrarian classes and cup products, which are like somehow classical invariants. Yeah, so these allow you to define more fancier invariants. So maybe I guess the idea is the following. So why? So you choose a metric. Okay. Then you count solutions. Okay, in the sense of most theoretical, you count the number of solutions of this thing in a suitable sense, and you get the chain complex. So this is called the Flirt chain complex. And once you take homology, you get some invariant of the manifold. Okay, so all these pieces, all the intermediate steps somehow involve choosing the metric. But the final, if you look at the whole procedure, is a topological. Okay, so the final outcome doesn't depend on the metric you choose. Okay, this is a construction group two from Heimer and Moore. Okay, so these are very vague, but it's in the spirit of all the Flirt theoretic invariants of counting solutions to nonlinear PDEs. Okay, and the nonlinearity here is key to get some interesting topological interesting invariants. Okay, this is called monopolar. Okay. So looking back at these equations, there's two kind of solutions. So the first one are called irreducibles, which are the case where psi is not identically zero. Okay, and these are the interesting ones. So they're somehow new and some interesting objects. But yeah, there's also the so-called reducible solution. So the reducible solution where psi is identically zero. Okay, and if you look a little bit what happens here when psi is identically zero, well, the first equation is solved automatically. Okay, just because this is linear, so it happens. And then this is some kind of quadratic term in size and some kind of polynomial. So this is also zero. So this tells you that the curvature of BT is zero. Okay, so we see again that in the set of solutions of this equation, there's two pieces, somehow the interesting ones, and this is the torus of flat connections. Okay. Yeah, so the picture, if you have maybe, is that, the solutions, the picture is that, there's this torus here. So this is the, an actual torus. This is Ty. Okay, this is the torus of reducible solutions. And then there's some other solutions floating around. Okay, this is the very rough picture. That's, this solution comes. And somehow, in this procedure, you try to somehow count the number of solutions properly on this. Okay, so here, the issue is that, this is somehow, if you think of it, some kind of Morse theory. So these are the gradient critical point equation for some kind of functional on this space. And this is the critical locus. So yeah, in general, you need to perturb things to make isolated points and do all the things you do in Morse theory. Okay, so yeah, so in particular, in this situation, when the torus is higher dimensional, you're never in a good transfer situation. You always need to perturb. So yeah, let me finish with saying that what the key point comes in. This said, so the key points. So if you have a metric, if G is spectrally large, then there are no irreducible solutions. Okay, so these points here that in general are there for a generic metric, they are not there once you have this condition on the first eigenvalue. And this is again, it sounds fancy, but just again an integration by part argument. Everything so this uses again the Lichner-Robbins formula that I mentioned before, and do some little slightly fancier arguments. So our set of solution is actually this. Okay, solution. All solutions. Okay, so all solutions are just these torus of flat connections. Okay, maybe let me focus on the case of the torus, but this is true in general. So the issue now is that I guess again you need to if you do Morse theory, you're familiar with the case where you do Morse dot theory. So you're not just have critical points, you have critical submanifolds, and your Hessian is non-degenerate in the normal direction, right? So this, it's a nice smooth manifold. But it turns out that it's not Morse dot. This is not Morse dot. Not the Morse dot. Okay, and the very nice thing is that Morse dot means that you're a smooth manifold, and the Hessian is non-degenerate in normal directions. Here the Hessian is degenerate exactly in the locus where the Dirac operator has kernel. So this was my This is my kappa. So kappa is exactly normal religion. Okay, and we know that it's non-empty by the similarity theorem, but yeah, so from the geometry you can tell that this is exactly the situation. And to conclude, yeah, I guess the idea is that from this picture, so here we count solutions. So from here, from this picture, you can compute the Floer homology of the topes. So from this picture, with care, so from here, maybe I'll draw again. So from here, together with the knowledge of this kappa, okay, kappa will be something like this. Okay, from here, this procedure that I was telling you a little explicitly gives you can actually get the Floer homology of the space. Okay, and this is simple enough. It turns out that from here you can actually determine the shape of the thing. Okay, so reverse the machine. The machinery from HM of P3, you get kappa is diffeomorphic to 2. Okay, from here, once you give me the shape of these things here, I can write down the chain complex that computes this thing here. And in this case, the Floer homology here is simple enough that from the shape of the Floer homology, you can get the chain complex and the K. Okay, so this last piece is a little bit of computation with spectral sequences and algebra. But yeah, I guess the idea is that the thing is simple enough that you can reconstruct the shape of this locus where the Dirac operator has come. And okay, I'll stop here.